just the uniqueness.
Mm-hmm.
So he just states fairly early in this section that every finite group has one of these composition series.
Normal series,
Then
right?
what he calls the Jordan-Holder
Mm-hmm.
theorem is the fact that two of them are essentially equivalent. But the factor groups are the same, the non-trivial factor groups.
Mm-hmm. Yeah.
And it's also a little bit more general because Dummett restricts only to finite groups, I think.
Okay.
Whereas the theorem that Rotman proves applies as long as there's a composition theorem or a composition series. It doesn't assume that the group G is finite. So it's a little bit more general that way.
Yeah.
Or a lot more.
I don't think I checked that 255 page thing for by Thompson. I don't think I saw this in other books as well.
Rotman, he doesn't mention the paper,
Mm-hmm.
but he mentions that it was proved in that there were, I've already forgotten what that result was, that everything of prime order is something. He mentions the fact that that was proved relatively recently, but he doesn't mention that it was 255 pages of hard math.
Oh,
I'm feeling pretty good about today's lesson. I'm looking forward to it.
Yeah.
It's only some stuff at the very end that makes no sense to me. Like the definition of a nilpotent group.
Okay.
I don't get it. So we'll see what we think once we get there.
Yeah. Yeah. I was looking at the problem 6 of last piece set again, and well, I'm trying to use what was that? The invariant factors and something else. I was looking through Rotman and trying to do it. I think it uses invariant factors, and I mean, I think it would make more sense if you do it in the like invariant factor way of doing. I mean, Rodman does it in two ways, right? So the latter, I believe, is going to be more, I don't know, closer to trying to prove the theorem.
I look forward to seeing what you write up.
Yeah.
I'm setting that one aside.
I think we're going to have a big review session, anyways, like early September or like end of August. We're going to review these 2 weeks, of course, and yeah, maybe then we'll talk
So
about
after modules or somewhere in the middle of modules?
I think after we've started modules, because we're starting modules next week, so yeah.
Yeah.
Okay. So we've got the goal is Jordan-Holder. We'll go through the round of Zazen House and then Schreier Refinement Theorem, and then hopefully everything will click. Yeah, I'll also pull up Jacobson if it is up somehow. Okay. So, yeah, Jacobson does it in like 3 pages, all of Jordan-Holder and Zazen House and everything. Rotman goes into details. Okay, so let's see. So first we'll define what a normal series is. So if you have a group G, you have a finite sequence of subgroups that contain each other, and the series terminates, as it's finite, it terminates at the group just containing the identity. Alright, so this is the sequence. You have G0 containing G1 containing G2. So your course is to use topological language, but yeah, to the smallest subgroup you have in the sequence is Gn, which is just the identity, right? And each of these like following subgroups are like normal subgroups to the previous one. So Gi plus 1 is a normal subgroup for Gi for all the indices, right? So this is the normal series, and what this normal series lets us have is it lets us have a series of factor groups. So your subgroups here in the sequence, contained within each other, are normal subgroups of each other. So you can have this series of quotient groups. You take the mod of these normal subgroups, respectively, and you have the series of factor groups, right, up until Gn minus 1 mod Gn, right? So those are the factor groups which we're going to use in the Zazen House lemma. Then the length of the series, so the length of the normal series is just the number of strict inclusions you have, right? So it's equivalent, of course, to the how many non-trivial factor groups you have, right? So non-trivial in the sense, if your G of your normal subgroups are not like the trivial subgroups, then your factor groups would not be trivial, of course. So that's the length. Then your group G is solvable if it has a normal series whose factor groups are cyclic of prime order, right? So this kind of is analogous to what we were doing before. We have the finite abelian groups and the cyclic direct sum of cyclic subgroups, whatever. So here our normal series, your group is solvable if its normal series has factor groups which are cyclic and have prime order. Okay, so that's the terminology that we need: the length, factor groups, how a group is solvable, and the normal series, of course. Before that, just give me a second. Okay, so yeah, Rotman doesn't delay anything. He brings up Zazen House lemma right away. So Zazen House lemma says that if you have 4 subgroups, A star, B, and B star, they are all subgroups of G, and the relation between the subgroups is that A is the normal subgroup of A star and B is the normal subgroup of B star, right? If that's the case, then what you can do is you can have A times A star intersection B. That is going to be a normal subgroup of A times A intersection, A star intersection B star. And you do the same for B, right? So you have B of B intersection B star intersection A is normal subgroup of B times B star intersection A star, right? And if that's the case, so you have these normal subgroups, you take the quotient, so you have these quotient subgroups which are isomorphic, right? And that's the lemma. So we'll have to look at how the intersections lead us to having the normal subgroups, and then how that leads to having this isomorphism that we need. Okay. So this Zazen House lemma is also called the butterfly lemma. The butterfly word comes from the fact that when you arrange all of these in this way of being contained within each other, and yeah, this is not really the categorical commutative diagram, of course, but this is more like just trying to have the relationships between the groups you have. So you have A of A star intersection B star, so this left side is all about A, yeah, right, and this one is all about B, yeah, okay, kind of like that. So you have A star intersection B star in the middle, and and what we're trying to do is this is A, wait, I think, right, so this is kind of like a typo, isn't it? Yes, A of A star intersection B. Right, yeah.
That's right. That's the middle one on the left.
Yeah. Right. This normal subgroup you have here. Yeah. Okay. I'm not sure if like having the asterisk makes it any easier. I found it like in Jacobson he has like the prime, and I don't know. I mean it's the same thing, but yeah.
One thing I found unhelpful is somebody who tried writing a proof using A, B, C, and D, so you could never remember what was normal and what. At least the star or the prime is better.
Okay, so right, so this thing is a normal subgroup of this. This is a normal subgroup of this, right? So this relation, this line here just represents being a subgroup or whatever. Now, okay, we'll have to go through the proof to understand how this whole diagram works and how it lets us have the isomorphism. But as he says, the isomorphism lets us have the fact that like you can get the right hand side just by interchanging the symbols A and B, right? So you can replace this A star B with A star and like A with B, and if you like repeatedly reverse the symbols, you're going to get exactly this sign. So you can get the other side just by replacing the symbols, as he claims. Okay, so we'll have to go through the proof of this. We're going to use the so this is going to be like the second isomorphism theorem, if you remember. Okay, we haven't got to the second isomorphism theorem because Artin said us that it's not necessary, but let me show you that from Dummett. He has all the isomorphism theorems. So this is the second isomorphism theorem, where if you have a group and you have two subgroups, and you assume that like A is contained within like the normalizer of B, then AB is going to be a subgroup of G, right? And B is going to be a normal subgroup of AB, and A intersection B is going to be a normal subgroup of A, and AB mod B is going to be isomorphic to A mod A intersection B. So this is an important theorem, unlike what Artin has said. So I would recommend you go into the proof here in Damage page 97, and the Zazen House lemma that we're seeing is going to be a generalization for this theorem. Okay. So this is Lang. I think Lang's notation is kind of better. He has like lowercase uv and uppercase uv.
Like that.
Okay, so let's see. So how he starts the proof.
One thing before diving in,
Yeah.
which is kind of fun to observe, is that on T set 3, you had us showed that a product HK is a subgroup if and only if HK equals KH.
Yep.
Remember that problem? So that's the reason that these products like A times A star intersect B star, that's the reason that all of those guys are actually subgroups of our group G.
Yeah, because
since, for example,
products,
A is contained in A star, it's going to commute with that intersection.
If A is contained within A star, yeah. Right.
If A is contained in A star, then A times A star is going to be equal to A star times A.
Yeah, the product becomes commutative, yeah.
Yeah.
Yeah, I think like that was directly from some proposition of Artin, isn't it?
It was just a homework problem that you gave us. It was on P set 3.
Okay, P set 3.
Yep.
Yeah, it is indeed, because we're going to manipulate that a lot, the product, and using the commutative. P set 3.
I thought it was P set 3. I looked it up this morning, so I'd remember it.
Oh, problem 1. Okay, yeah, that's from Artin.
Oh,
yeah.
Here it is. It is. And P set 3 also had stuff on the commutator subgroup, which we're going to see later. So P set 3 was a good introduction to stuff that we're seeing today.
Good to know. Things are lining up. Yeah. Okay. Yeah. The first problem of P set 3 essentially deals with if you have subgroups of a group, then the product set is going to be a subgroup of G, if and only if the product of the subgroups H and K are commutative. Right. Okay. And problem 3, the last problem, is still unsolvable for us. We're still working on it. It also came up in P set 6, but we don't have a solution yet. Okay, so shall we get into Zazen House? So they first deal with the first normal subgroup condition that we have to prove. So they show that A intersection B star is a normal subgroup of A star intersection B star. Alright. Okay. So we have to show that works. So if you have an element C in this intersection, A intersection B star, and you have another element X in A star intersection B star, then you see at the conjugate of a C with respect to X. So if you see the conjugate x c x inverse, it's going to be in A intersection B star, because if that works, then you have A intersection B star as a normal subgroup of A star intersection B star, right? So for every element, you can have the conjugate within the subgroup. That's the definition of normal subgroups. Now, this conjugate that we consider x c x inverse is in A because C is in A, right? C is in this intersection, so C is going to be in A. Thus, this thing is in A, right? Now x has to be, x is an A star because x is in the intersection, so x is an A star, and as all these conjugates are in A, and everything that you're taking conjugate with respect to is an A star, that is x's, then A is going to be the normal subgroup of A star. Make sense? Now, x c x inverse, the conjugate, is in B star because C is in B star from here, and X is in B star. Right? C and X both are in B star, so this conjugate is also going to be in B star. Hence, from both the sets, you get the condition that your conjugates are going to be both in A and in B star. Right? So we just showed that A is a normal subgroup of A star, and the conjugates are also in B star, right? So A intersection B star is a normal subgroup of A star intersection B star. So this, the first claim that we did, holds. Alright. Now similarly, we have to prove the other way around. So this here we had the asterisk on B, so we replace the asterisk from B to A. So we need A star intersection B to be a normal subgroup of the same group, right? So how that works is the same way you did here. He doesn't repeat the same argument, but essentially you're going to take an element from here, is going to be in A star, then you see the conjugates are going to be both in A star and in B star. So that works. Now, okay, so you have these two conditions. Now, if you have the asterisks on both both A and B, and then you take intersection, is going to be the group that contains the normal subgroups where you have the asterisk on each of the subgroups, right? That's a nice way to remember it in terms of where the asterisk is. Right. So then the subset that we define is the product of these two normal subgroups that we just got, right? So if you take the product of A intersection B star and A star intersection B, both are normal subgroups, then this subset D is going to be a normal subgroup of this main group A star intersection B star, right? Because this subset that we just defined is generated by the two normal subgroups of this, right? Okay, I guess it makes sense until now. Now what we try to do is we try to have a map which goes from here to here, right? So we want A of A star intersection B star to A star intersection B star mod D. And why we need that is because the D is this special product of these two things, right? Sorry, what was that? A star intersection B and A intersection B star. So when you take the mod, whatever you're left with should be isomorphic to taking the mod of these things, right? So that's the goal. How you do that? Well, you define this map which goes from here to here, and what it does, it takes AX. So A, the small a, is an element of the subgroup A, and it maps it to XD, right? So X is always an element of A star intersection B star, remember, right? So it takes AX to XD, and D is just your subset. So XD here is a coset in this quotient group, right? Now they show that phi is a well-defined function, because if AX is equal to like some other A prime times X prime, then when you take the inverses of these primes and multiply, they happen to be the same. So what this means is that your function is well defined in taking these terms to the other side, right? So phi is well defined. Then the next goal is phi is a homomorphism. So you take two things, AX and A prime X prime, you have the product, then that is equal to Right, give me a second, I'll be right back. Okay, I'm back. So we have to show that it's a homomorphism. They introduced this double prime. So A double prime is A times the conjugate of A prime, right? Okay. And that works because your conjugates are in A, and that is because A is a normal subgroup of A star. Okay, so what they show that if you have two elements multiply, then you're going to get phi applied on the multiplication. Okay, so it's going to do the same. So phi of AX times A prime X prime is equal to phi of this thing, A double prime X X prime. So A double prime is just this A times the conjugate, nothing else. Right. Then that is equal to X X prime D. That's by definition of this function that we defined. It takes ax to xd. So here you have a double prime, and that disappears. You're left with xx prime times d. So this is the coset of the quotient group that this phi maps to, and that is equal to this is xx prime d, right? So you can write that as phi of ax times phi of a prime x prime, because you know you have phi of ax, that is going to give you xd. Phi of a prime x prime is going to give you x prime d. So xd times x prime d is just the same as xx prime d, right? So that's how it's a homomorphism. Then you have to check that it's a surjective homomorphism. They don't do that here, but to show that it's surjective, you really have to just check that every coset in here can be every coset in this quotient group gets hit by these ax's, right? So each of the coset has to have this ax in here, and that makes sense quite trivially, but you can check that. The kernel of this homomorphism, let's see what the kernel is going to be. The kernel is going to be, let's think about what stuff from here will get to the identity in here. Well, the kernel is going to Alright, so your D, remember what D is. D is the product of A intersection B star times A star intersection B. D is the product of these two things. And these two are normal subgroups. We want things in here which get to the identity when you take this mod D. So right. You have A times A intersection A star intersection B star, right? So these A axes, if they get mapped to the identity, then what you need is something to multiply so that this disappears, and those would be the elements from here, A star intersection B, right? And this you cannot take this one because this is A intersection B star. That you could take that if you had B in here instead of A, alright? But as you have A, you need A star intersection B, and the elements from there multiplied by A, right? Right, remember A times this thing is going to be a subgroup of this, right? I hope that's clear. It's pretty straightforward, but yeah, A times A star intersection B is going to be a subgroup of this. We don't know if it's the normal subgroup, but it's a subgroup indeed. So elements from there are going to look like Right. So they're going to look like these C's you have here. Like this is A intersection B star, but this is the same for A star intersection B. But here instead of AX, you have AC, and right. As this is the normal subgroup, so you would have the conjugates. So essentially, after multiplication, you'll get the identity, because the conjugates, the inverses and the conjugates will cancel each other, and you'll be left with the identity, I believe. A strict proof is necessary if you want to go to the details, but yeah, so the kernel would be this. And by the first isomorphism theorem, as we have the surjective homomorphism between groups, and between this group and its quotient, we're going to have an isomorphism, right? Remember, between this and this, right? That follows directly from the first isomorphism theorem that we saw in our early group theory days. Okay, so this is a very short proof, and I believe it doesn't really give that much of detail. Lang introduces more terminology. Actually, he has this tower of a billion groups or something, and he says that these towers are equivalent or the same. So I'm not sure about that. That was the Zazen House lemma. Let's see. Right, so like the goal is, once you, so like this was what I was saying. So this was the phi morphism that they were trying to show, and so they showed that f is well defined, f is clearly surjective. They show that f is an epimorphism. Now for the kernel argument. Now this AC, C here is an A intersection B. So the notation here is a bit different, but the idea is the same. So AC is going to be in the kernel if and only if your C here is from D, right? So that's what I was saying, that for to have things from the identity, you have to replace this X, not to take it from A star intersection B star, but you have to take it from D. And in D, you can't take it from here, but you're going to take it from here. Okay.
Yeah, I think that once we get our head around what the kernel is, everything else is good.
Yeah, I mean, once you get the kernel, you have the normal subgroup. You apply the isomorphism theorem, and you're done.
Then swapping all the A's and B's, you get this stuff on the other side, the other wing of the butterfly.
I'm quite interested in how Lang does it, but I'm kind of intimidated by how he does it. Maybe he has this Right, so okay, so this sequence of subgroups are, so instead of series is saying that is a tower. Okay, there's nothing else. And your tower is normal if each of the corresponding, following groups is normal in the previous one, right? So we saw that already in Rotman. Right, so our tower, the series, is abelian if it is normal and each of the factor groups is abelian, right? So that is, you have the cyclic condition. Okay. Then he says that you have a refinement. Yeah, sorry.
This seems to be looking forward to what we're going to see a little bit later in this section about doing refinements of normal series. It's the reason that we're doing Zazen House, so that we can prove that two series have a common refinement.
Yeah.
More or less. I mean, they each have a refinement so that and a correspondence between the non-trivial factor groups. Actually, between all of them.
Oh, wait. Wait, is this similar to what we were seeing in like Rotman about the, what was that? I'm forgetting. Something related to the upper triangular matrices, right?
Yeah, the upper triangular with 1 on the diagonal.
Yeah, and everything else is above the diagonal we have the upper triangular matrices, and he called it something, right? I'm forgetting the term.
Called it UT. Do you remember what it was? Wasn't it UT?
Yeah, it was UT.
It wasn't upper triangular.
No.
Like unitary triangular, something like that.
Something like that. Yeah. Yeah, Lang also does the same. He proves, I think, a few things before Zazen House. So this theorem, which says that if you have a group and H is a normal subgroup, then G is going to be solvable if and only if both the normal subgroup and the quotient group are solvable.
Rotman has a lot of those facts that he sprinkles in, saying either they've been proved before or that they're future exercises. Just showing that normal combinations of whatever category of groups gives you something else which is in the same category. Using the word category informally, not formally. Like, every subgroup of a solvable group is solvable, every quotient of a solvable group is solvable, blah, blah, blah. So they...
Okay.
It seems to be a checklist that they want to go through when they define this new type of group, or combinations of groups of that sort, also of that sort.
Yeah.
That's still coming up in the section we're in. We're going to see it.
So Lang. So he explains the diagram at least. Rotman doesn't do that. The combination of groups and factor groups become clear if one visualizes the following diagram of subgroups, which gives its name to the lemma. You have U intersection V, U, V. Okay, so I think like this is like, I mean upside down of what Rotman has. Rotman has like A and B like down here or something. Oh, that's U and B. Wait. Okay, so A and B here are okay, lowercase u and v. Okay, I got confused with capital N and capital V. The intersection of two line segments going downwards represents the intersection of groups. Okay. The two lines going upwards meet in a point which represent the product of two subgroups. We consider two parallelograms. Okay, so these arrows are for the sake of like parallel lines, so this is a parallelogram.
I know those equal marks are showing the isomorphisms also.
Yeah.
I'm going to vote for Lang in this case, is making a better use of the diagram.
Yeah.
Rotman seems to grudge putting the diagram in there in the first place. He doesn't like it. And I'm going to speculate that he doesn't even put it in the new edition, but I'll go hunt for that. You don't need to do that.
So what he says is that the sequence of factor groups in towers are the same after isomorphisms. Right, so he has this group and he has the towers, and he makes the case that the factor groups are the same, and yeah, so this is like one step towards the Schreier refinement theorem and the Jordan-Holder stuff. But for this Zazen House, I believe he's done here. Okay.
I'm wrong. He does put it in the third edition.
He does put
he
it?
still complains about it.
Okay. Seems like nothing has changed over the years. Okay, so let's get to Rotman back. So we proved the Zazen House lemma. The exercise for the reader is that they have to check that from this Zazen House lemma you can prove the second isomorphism theorem. It would not be that big of a deal. I mean, I think it's going to be easy. If you just replace the A star, B star with the correct subgroups and normal subgroups. Yeah. So more terminology. A composition series is a normal series, all of whose non-trivial factor groups are simple. Right? So if you have a normal series whose non-trivial factor groups are all simple groups, then you have a composition series. And the factor groups of this composition series are going to be called the composition factors. Okay. Right, so this I believe is where Dammit departs or something, or starts, because here you'll see that the composition series is not applicable for each group, right? So but it's always applicable for finite groups, which are going to prove in this proposition. So I believe Dammit does it for the case of finite groups because all of them have the composition series?
Lemma doesn't prove it, but he gives an exercise and he only asks it be proved for finite groups using induction.
Okay.
So this proof that Rotman gives is a lot slicker, especially since he's doing it instead of making the reader do it. But I think that I kind of appreciate what Dummett's doing because the induction kind of gives you an idea how these composition series work.
Okay, I'll have to look because I don't think I have an idea about how induction would work here. I mean, you're going to like have the induction applied on the containing and like work from there.
Yeah, you can kind of do it on the order of the group. If you assume that all groups of order less than whatever have composition series, then let's say that you have it, the inductive step. Let's say that we now have a group of order n. Well, either that group itself is simple or it has a proper normal subgroup. If it has a proper normal subgroup H, then H, since it's smaller, has a composition series using the inductive step. And also G mod H has one. Because G mod H is also smaller. Then you use the lattice isomorphism theorem or whatever to go from the composition series for G mod H into a bunch of normal subgroups between G and H. So H down is taken care of by induction, and between G and H is also taken care of by induction plus the lattice isomorphism theorem.
Okay, so he doesn't do that in...
And that kind of fits into the theme of this chapter.
Okay.
Which is, if you know about... It's the extension problem that he describes later on. If you know something about a group and the extension group, I mean, how many possible groups satisfy that?
He has an example on that.
If we keep going, we're going to run into that.
Yep. Okay. Yeah, we've got still a decent amount of things to be covered. Okay, so we're done with Zazen House. We defined what a composition series is. The next proposition says how every finite group has a composition series. If the proposition is false, let G be a least criminal. That is, G is a finite group of smallest order that does not have a composition series, right? So it's the least criminal. Now G is not simple, otherwise, because G is going to contain, the trivial group, then that itself is going to be a composition series. Okay, I'm kind of like not that happy with this symbol for subgroups or whatever, but okay. G has a proper normal subgroup. Okay. We may assume that H, a proper normal subgroup in the sense that it's not the trivial, I guess. Yeah. We assume that H is a maximal normal subgroup. Okay. So if H is a maximal normal subgroup, then G mod H is going to be a simple group. I guess we've done this before. But the order of H is less than the order of G. So, okay. So that implies H does have a composition series, right? If that's the case, you take this series of H, starting from H0 containing H1 containing up until the trivial group, and then G is going to contain G contains H. It's a normal subgroup, so it's going to contain this whole series as well, and then you get a series for this G, which is contradiction because we assume that it does not have a composition series, right? So, and this is a composition series because your factor groups are simple, and it's a normal series. So, yeah. Now, so that was why we need the case of finite groups. A group G is going to be solvable if it has a normal series, its factor groups as cyclic groups of prime order, right? Because that's what we said in the definition of what's a solvable group. Now, as cyclic groups of prime order are simple groups, yeah. Then a normal series, as in the definition of solvable group, is a composition series, right? So if you have like a group that is solvable, then the normal series that you have there is going to be of cyclic groups, and they have all orders in prime, and what that means is that their factor groups are simple, and that implies that it's a composition series. So if you have solvable groups, you have composition series. They go hand in hand together. Right. He gives kind of like this example. If you have G as a cyclic group of order 30, then you have this kind of sequence, sorry, this series. You have G is equal to this A, which contains the cyclic group of A square, which contains the cyclic group of A to the 10. Okay. And the factor groups that you have would be A mod A square, which is just isomorphic to integers modulo 2. We have proved that. A square mod A10 is integers modulo 5, and A10 mod the trivial group is integers is just A10 and is isomorphic to integers modulo 3. And well, okay. So this is a normal series of this cyclic group of order 30. Another normal series he gives is like this, whose factor groups are integers modulo 5, integers modulo 3, and integers modulo 2. The same thing we have here, but you have these cyclic groups different. So this case, that this thing that just happened, the factor groups being the same in the case of two different series, he says that it's going to be actually, this is going to be actually the main statement of Jordan-Holder theorem, right? So different composition series of the same group are going to have the same factor groups. Okay. Now we're going to define some more terminology before we get there. So two normal series of a group G are going to be equivalent if there is a bijection between the sets of non-trivial factor groups of each, so the corresponding factor groups are isomorphic. So essentially, if you have a series normal series, then of a group, then you have a set of non-trivial factor groups. Then if you have two series of the same group, so you have two sets of non-trivial factor groups. So if you can have a bijection between these two sets, then you're going to make each of the factor groups isomorphic to each other, and then your those two normal series are going to be called equivalent. Okay, so the Jordan-Holder theorem, he says it in advance that I need two composition series of a group are going to be equivalent, right? Okay, so before that we have to prove the Schreier, I don't know, the Schreier in refinement theorem. So refinement is when you have a normal series, but the refinement of that is going to be another series. Wait. Yeah, a refinement of a normal series is a normal series G with this having the original series as a subsequence.
You mentioned topology earlier. This is like a finer topology.
Yeah.
Finer in that sense.
Okay. Yeah. Topology reminds, of course.
Or a finer partition.
So something like, if you remember, something like the box topology, or the I don't know how I'm forgetting all this. The Euclidean topology, the standard topology, is going to be like the coarsest one. The finer ones are the some other conditions you have. But yeah, so refinement of normal series is going to be a new normal series obtained from the original. So it's induced from the original by adding more subgroups to it. So essentially, you increase it and make it more quote-unquote finer. Okay. So yeah, the Schreier refinement theorem says that any two normal series like this of a group G have equivalent refinements. So if you have two normal series of a group, then their refinements are going to be equivalent, right? And the proof of this uses the Zazen House lemma, so we're going to see how that works. But after we're done with this refinement theorem, we can jump directly to Jordan-Holder theorem, which of course is just follows directly from the refinement. And then we'll probably see a few examples. Okay, so what they do, we insert a copy of the second series between each pair of the adjacent terms in the first series. So for each index I, you have now, instead of like having one index, they have two indices. So Gij is equal to Gi plus 1 times Gi intersection Nj. Alright, so now they're kind of like trying to include terms from the second, so that they, in a way, they can write those things in the first series. Alright, so Gij now becomes Gi plus 1 times Gi intersection Nj. Now and it's well defined as, like, in the sense that the containing these subgroups are well defined, because Gi plus 1 is always a normal subgroup of Gi, right, in the normal series. So Gi0, so when J is 0, you have a Gi plus 1 times Gi intersection n0, right? And n0 is equal to g, right? So this becomes gi plus 1 times gi intersection g. Gi intersection g is just gi, right? There's nothing else in common. So because gi is equal to g, of course. So gi plus 1 times gi, and that is equal to gi, because gi already includes gi plus 1. It's the normal subgroup. In that sense, you define all these things, so different indices. So gik is equal to gi plus 1 times gi intersection nk. Now nk is the last term here, so it's just a trivial subgroup. So this becomes just gi plus 1, because this whole thing blows up and vanishes, because you have the trivial subgroup. So what we were able to show was that between gi0 and gik, you have all the things n0 up until nk, right? We were able to arrange the entire the second series between gi0 till gik, right? So that's that works out. Now, so this is a refinement, right? Now right, so this what we got here is going to be a subsequence of the original series that you have here, because of course, because everything everything in GI, the original series, stays like that. It's just that between GI0 to GIK, we added these things. So it's a subsequence of the original series, right? So what you can do is you can do something similar for the second series, and try to have try to have the same kind of subsequence that you needed for a GIK.
So for both the G's and the N's, we found a sequence of groups. The only thing we haven't done yet is we haven't shown that it's a normal sequence. That each of these guys is a normal subgroup of the one that came before.
And
that's where we're going to use Zazen House, as well as showing that there's a one-to-one correspondence between the quotient groups.
Okay.
Or the factor groups.
Alright, so this NPQ is equal to NP plus 1 times NP intersection GQ. So instead of, just like we did here, we're putting in the G's between the N. So we get, the subsequence. Now for each IJ, the Zazen House lemma, for the 4 subgroups, right? So you have the subgroups that you got from this kind of subsequence generation. GI plus 1 is a normal subgroup of GI, and NJ plus 1 is a normal subgroup of NJ. So from this Zazen House lemma, we know that you can have this nice isomorphism between the intersections and the quotient groups. So gi plus 1 times gi intersection nj. So this is this thing, right? So that mod gi plus 1 times gi intersection nj plus 1. So instead of nj, you have nj plus 1, because that's this subgroup. Okay. So you have this isomorphism from Zazen House, and what this lets you have is lets you have this bijection between these two things. So gij is just the abbreviation for this, and gij plus 1 for this. So gij mod gij plus 1 is isomorphic to nji mod nji plus 1, right? So you have the isomorphism there, you have a bijection, and these quotient groups, if you remember, they represent the factor groups of both the sequences, right? For both the normal series. So these factor groups now have a bijection between each other, and thus the two refinements are equal. Yeah, that makes sense. On Jordan Holder, so Jordan Holder, the statement is that any two composition series of a group G are going to be equivalent, right? So in particular, the length of a composition series, if one exists, is an invariant of G. So essentially, if you have the length of a composition series, so if you can get a composition series out of a group, and if you like measure its length, that is the number of non-trivial factor groups, then that length, that number is going to be invariant through all other composition series that you're going to get from G. So the proof of this directly follows from the refinement theorem, because the refinement of a composition series. So here, remember, we had a normal series, but if these two series are like composition series, then yeah. So if you have them as composition series, then any refinement is going to be equivalent to the original composition, because again, if you have composition condition, then all the groups, the factor groups, are simple, right? So any refinement that you try to make to these composition series is going to be equivalent. So essentially, you can apply this Zazen House lemma again to any subsequence, and you will see that it's the same. So then you apply the refinement theorem, which says that any two composition series are going to be equivalent because they're equivalent to the original composition series. So that's the Jordan Holder theorem. We have a few examples to go through, but yeah. The bibliography here of Lang seems interesting. I have heard this Gorenstein book, but I have never checked it. He has a few groups on finite classification of finite groups, so maybe worth checking. Okay. So that was Jordan Holder. So okay, let's get to examples, I guess. So this corollary says that every integer greater than or equal to 2 has a factorization into primes, and the prime factors are uniquely determined by the integer. So that's the fundamental theorem of arithmetic, and you can see that in terms of what we've done. Didn't we do something about the fundamental theorem of arithmetic with finite abelian groups? Remember me, JP? Remind me, JP. I mean, I'm not sure if I remember, but I think he had something in exercises related to that.
I know we've seen it before, but I don't remember how it was proved when we saw it before.
Yeah. Maybe it
This
was
is
something like the
taking a
psychoanalytic.
sledgehammer to a nail, though. Right?
I mean that's like the goal of maths, right? So you can build generalizations so that like you no longer work with numbers. But yeah. So the proof is pretty straightforward. Your integers modulo n is finite. Okay. So you have these factor groups S1 till St. Now we've seen this before. I guess we've seen this before in Arten, but I believe Rotman does it in in his first chapter on groups. That an abelian group is going to be simple if and only if it has a prime order. Now n is the order of integers modulo n. Okay, is the product of orders of factor groups. 5.36 exercise 287. Okay, so it's done future exercise. Okay, I don't really see the point of like writing a proof if it's using a future exercise. Okay, so that's Jordan-Holder theorem. Sorry, the corollary of the Jordan-Holder theorem on the fundamental theorem of arithmetic. So essentially, the product n is going to be the product of the orders of the factor groups that you have there, S1 till St. Now the factor groups are simple, and you have like prime orders there. So n is going to be a product of primes. Now the Jordan-Holder theorem has the uniqueness aspect, right? That a composition series of a group is unique to itself. So this series of factor groups, the set of factor groups that you have is going to be isomorphic to any other set of factor groups, and these factor groups give you the prime numbers for the prime decomposition. So essentially, the set of primes that you're going to have, they're going to be unique. Only the exponents are going to change. Right. A few other examples. Okay. So he gives this example of the general linear group containing 2 by 2 invertible matrices from a field of 4 elements. So he defines the determinant function from G to the multiplicative field I mean the multiplicative group of the field, and this multiplicative group of the field is isomorphic to I3, integers modulo 3. Okay, so that's the determinant. I mean, it makes sense. You know, the multiplicative group, because you have 2 by 2 matrices, so the determinants, are going to look like the, it's going to be like a chain of like addition and subtraction of like product of two elements, right? So like AB minus CD, and it repeats. So this F4 cross has those elements. Okay. Okay. Now since we have the kernel, well, the kernel of this is going to be just the normal subgroup under GL, which is this simple linear group. Sorry, the special linear group, whose determinant is 1, containing the matrices of determinant 1. So you're going to have this normal series going from GL to SL to 1, right? And the factor groups are I3. The factor group of this is going to be 2 SL, the same thing. Okay. Right. Okay. So this series is actually not just a normal series; it's a composition series. Okay. Now you apply the Jordan-Holder theorem again, and you'll get that you know. All right. So yeah.
Something I didn't get before, but I think I might get now, is let's say that we're given a group and we're trying to prove that it is not solvable. Well, it's hard to prove a negative. You'd have to show that there does not exist a composition series where all the quotients are, what's the requirement? Abelian? Abelian of prime order? Is that what solvable is? Yeah. So what Jordan-Holder says is that if we can exhibit any composition series which contains a factor group which is not abelian of prime order, then that's good enough. Because if you find any other decomposition or any other composition series, it's going to have up to order the same factor groups. So if I wanted to show that GL2 F4 is not solvable, I don't have to consider all possible composition or series for it. I just have to exhibit one which has a factor which is not abelian of fine order, of prime order.
Okay. Yeah, makes sense. So essentially your GL here of 2 by 2 matrices is not solvable, not a solvable group. Okay, so the history behind this is that Jordan first proved that the orders of the factor groups of a composition series depend only on G and not upon the composition series. Okay, that was in 1868. 21 years later, Holder proved that the factor groups themselves, up to isomorphism, do not depend upon the composition series. 21 years. I thought this was like some collaboration stuff, but okay. I guess we have this last thing about extension. He brings up the commutator subgroup. I guess we're going to need this when we do Lie algebra. Of course, Lie algebra has exactly this, but do we need it like anytime before in modules? I don't think so, I guess. Because commutators are like the things on which you have Lie groups and Lie algebra, but okay, anyways, we're going to need it. And anyways, commutators are needed in algebraic topology, I guess. So we'll see. Definition again. If you have a group and you have a normal subgroup, then G is going to be G is called an extension of K by G mod K. Okay. Right. So you can extend the normal subgroup K to G through G mod K. Okay. That's the extension. The exercises again, he says that if you extend a P group by another P group, you're going to get a P group. Okay. And the proposition 4.24 says that extension of one solvable group by another is itself a solvable group. I'll have to check that, I guess. I think it doesn't say this here. Okay, so we have some more stuff. Example 5.55. The direct product is an extension of K by Q. The direct product is an extension of K by Q, right? That's because you can have K as right, and K across Q is an extension of Q by K. Okay. S3 and integers modulo 6 are extensions of I3 by I2. Yeah? That's because I3 cross I2 is just I6. Right.
And also in S3, the subgroup of 3 cycles is normal. And the quotient of S3 by that subgroup is I2.
Yeah. Right, so for any given pair of groups, you can have extension because you have the direct product. But there may be non-isomorphic such extensions. Okay. Hence, if we view an extension K by Q as a product of K and Q, then this product is not single valued. Okay. The extension problem is to classify all possible extensions of a given pair of groups K and Q, right? So how many extensions you can have from a given pair. If you have G as this normal series of K, and its factor groups are the quotient groups Q1 till Qn, just like before. Now Kn is 1, so then Kn minus 1 just before this is just equal to Qn, because Qn is equal to Kn minus 1 mod Kn, but Kn is just 1, so that's going to be Kn minus 1. So Kn minus 1 is equal to the factor group Qn. Kn minus 2 mod Kn minus 1 is Qn minus 1, right? So what that means is that you see, Kn minus 2 can be an extension of Kn minus 1 by Qn minus 1. That's the definition of the extension, right? You have the quotient group. Okay, so he says something interesting. So if we could solve the extension problem, right, so that is, we can classify all possible extension of a given pair of K and Q, then we could recapture. So recapture Kn minus 2, the extension. You can recapture Kn minus 2 from the given pair Kn minus 1 and Qn minus 1, right? And Kn minus 1 is just Qn. So you can recapture Kn minus 2 from Qn and Qn minus 1. You can do the same repeatedly. So if you have Kn minus 3 as an extension of Kn minus 2 and Qn minus 2, then if you can solve the extension problem, you can recapture Kn minus 3 from Kn minus 2 and Qn minus 2, right? And Qn minus 2 is just Q, so Kn minus 2 is just Qn minus, Kn minus 3. Okay. Alright, so you can recapture Kn minus 3 from Kn minus 2 and Qn minus 2. Now Kn minus 2 in this previous thing can be recaptured from Qn and Qn minus 1, right? So you have Qn minus 1 and Qn minus 2. So you can recapture Kn minus 3 from Qn minus 1. They both give you Kn minus 2, and then you can use it to get Kn minus 3 with Qn minus 2. Okay, just a lot of symbols, but the gist of this makes sense. So climbing up the composition series in this way, we end with G as K0, so you get the whole group being recaptured in this sequence of Qs, right? Thus G is a product of the factor groups, and that makes sense, right? If you think about this, factor groups are factor groups. So when you product the factors, when you have the multiplication of the factors, you're going to get the number. Here the number is a metaphor for the group. Now if this normal series that we just took for G is a composition series, then you can apply the Jordan-Holder that the factors in this product are going to be unique for G, right? So the composition factors are going to be unique. So if you can survey all finite groups, if we can know you can survey all the finite groups if we knew this finite simple groups, because you have the composition series, so your factor groups are simple, and you could solve the extension problem. Okay, I don't know what it means by solving the extension problem, but I believe it just means classifying all the extensions. Now all the finite
That's right.
simple groups were classified in the 1980s. Ah, okay. All the finite simple groups?
Is that 255-page paper?
I don't know.
Oh, no. The 255-page paper was the
Thompson.
one about groups of prime order.
Yeah.
I think I've heard the classification of all finite simple groups is more like 10,000 pages.
10,000 pages?
Approximately, yeah. That's the number that pops up.
Ow. That's interesting.
Didn't we see that somewhere? That it was a lot spread over lots and lots of different articles.
Wow. Like one wonders how much work has been done just in this tiny area of finite simple groups.
He showed us in Lang's references, there's one author, and I noticed that the 4 different things that he published were all like 10 or 15 years apart. So there was a huge spread those different articles on finite groups.
I see. Ah, that Lions
so it looks
and
like
Solomon,
that was a hot topic to be working on.
Okay, yeah. Yeah, I think I saw Solomon and Lang. Yep, R. Solomon. Brief history of the classification of the finite simple groups. Interesting paper to check.
I was noticing the Gorenstein, 68, 82, 83, 86.
I see. Yeah.
And then 2001, brief history. I guess that'd be the place to look, huh?
Yep, we're learning about not just like some old school stuff. This is very wow. Like if you check the Wikipedia page of classification of finite simple groups, as recent as 2012, okay, 2012, they had some computer checked version of White-Thompson theorem, that 255-page stuff. They did that with a computer. Cool stuff. I'm not sure if we have enough background to check. I'm not sure, but it will be nice. So this theorem, one of the deepest theorems in mathematics, gives a complete list of all the finite simple groups along with interesting properties of them. One has to make a website of all this. It will be something amazing to check, isn't it?
I'm just hoping that as time passes, someone would read all of that and simplify it so it can fit into a textbook.
Yeah.
Well, maybe I'm a bit too optimistic, but
this actually looks interesting, damn. So in a sense, the extension problem has also been solved because they were able to just trim down all the finite simple groups. Okay. In chapter 10, we'll give the solution to the extension problem, is it? Which describes all possible multiplication tables for extensions. This study leads to cohomology. Okay, cohomology of groups and the Zazen House theorem. Cool stuff. I believe, like, I mean, you know, if you're taught something like this in grad school, yeah, I mean, if you're, I mean, if this is, you know, like in a general algebra course, and believe like someone is going to be interested in this, and you know, maybe write his dissertation on groups. Okay, so we are not going to get into the cohomology of groups. The farthest we're going to get is, I mean, not in this course even. I think in algebra topology we're going to get into cohomology, but not of groups, I guess. I think I saw something like that in Jacobson. Right, so he has a section on extension of groups, and that deals with some cohomology. God, I can't pronounce that.
Even Dummett has a chapter on group cohomology.
Right, nice.
I mean, it's an introduction, just like he does introduction to a couple of other things, like a one-section introduction to algebraic geometry. But I mean, for an introductory book, it's at least something he thought was worth touching on.
Yeah, he touches upon like a couple of things. Like I guess he has representation theory and algebraic theory, so algebraic geometry, and what was that? Some homological algebra, I guess. So yeah, this extension of groups seems interesting. I don't know. We're going to, maybe we can hope a homological algebra course in the farthest future. Okay, so he gives some more history, I guess. Yeah, right, so this Burnside theorem, this P to the M Qn, is actually related to the solvability of groups, and it's also something that appears in representation theory. So, Burnside. It looks like they have, right, I guess we're going to do something like that in our course, this course. Let me look at my schedule again. The last lecture. Yeah, we're going to do chapter 5 of Jacobson, volume 2, section 1, 2, 3. The chapter 5 is classical representation theory of finite groups. Right, so he deals with these things. I don't think we'll go that far, but I don't know. We'll see. Alright, so we'll have representation and matrix representation of groups, then complete reducibility or something, then application of representation theory of algebras. I don't know. I'm kind of lost. I was thinking of replacing this representation theory with something related to number theory or something, but people said that they want to do number theory, you know, separately. So yeah. Okay, so what else do we have? This commutator stuff, and then we're done. Proposition: every finite P group is solvable. Okay. If your group is abelian, okay, that is straightforward. Otherwise, if you look at its abelian subgroup, that is the center, that is a proper non-trivial normal abelian subgroup. Yep. Now the center is solvable, right? Because it is abelian, and if you take the quotient group of G mod the center, that is solvable, right? And by induction on the order of G, okay, so you start from proposition 4.4. I think like we'll have to check. I think he mentioned 4.24 before as well, but yeah, every
I think
finite.
the idea is kind of what I was saying earlier,
Yeah.
that either G, let's assume that all groups of order up to the order of G are solvable. Then when we look at G, either it's already solvable or we form this quotient, and the quotient is smaller. So that means that the quotient is solvable, and then the lattice isomorphism theorem gives us our decomposition of G.
Yeah, essentially. This looks like the primary decomposition and like P primary components of a group that we were looking at, isn't it? In finite abelian groups. If you're like, what is that? If your group was not finite, if your group was not P primary, then you look at the P primary component, and then you do the P primary decomposition. Okay, so we have this commutator stuff. Let's see. If G is a group and you have two elements from the group, then the commutator is this element represented by x, y in close brackets as xy, x inverse, y inverse. So that's the commutator. If x and y are subgroups of a group G, then then the commutator of these two subgroups is defined as the cyclic group generated by the commutators for each pair of elements from the two subgroups, right? So in particular, the commutator subgroup G prime is this subgroup generated by all the commutators. Now, two elements in a group are going to commute if their commutator is commutative. Yeah. Okay, so proposition, if you have a group, the commutator subgroup G prime is a normal subgroup and your quotient group is abelian. If you have a normal subgroup of G, then and your quotient group is abelian, then the commutator subgroup is going to contain in H. And this proposition's proof is not that hard. You just have to play with the inverses and arrange them so that you can have the commutator. Right. So just pretty much manipulation.
That's the one where part 1 was on homework set 3, problem set 3.
Oh, right. Yeah, because
so you already gave that to as homework.
Okay, that's good. What was that? Problem number 6, right? In a Luffy. Okay. This is nice. Things are kind of lining up. Yeah. a commutator subgroup. Yeah. So a group G is abelian if and only if its commutator is the trivial subgroup all the time. If G is a simple group, then the commutator subgroup is 1 or the group itself, right? Because we need it normal. And a few more stuff. But okay, I think like we should be done with this derived series, and that will be it. I don't even know why does he do this. I didn't think I saw derived series elsewhere, but he has some things to say about it.
I tried looking up something briefly, and there's all kinds of literature on the central series, but since we're going to be leaving this book after this section, I don't know that we're going to see where it's put into use.
Okay.
Because the way they're defined just looks weird, not knowing what it's used for.
Yeah, your indices seem to be now moved up. You have G0 containing G1, G2 up until Gi plus 1. It continues. G0 is G, and G1 is the commutator. Gi plus 1 is equal to Gi. Okay, you take the commutator of Gi. Okay, so you're taking the commutator of each preceding group, okay, and getting the new group. So your the chain here is of course like being contained, but it's not just normal containing. It has a condition that everything that is contained is a commutator group subgroup of the thing that is contained, the thing it is contained within. So the derived series can be used to give characterization of solvability. G is solvable if and only if the derived series reaches the identity.
I didn't look it up. Do you know what he means by fully invariant?
Fully invariant, I believe, in the sense that your commutator like Gi, wait.
So we know that G2 is normal in G1.
Yeah.
Since it's the commutator subgroup of G1. This is saying that G2 is also normal in the original group G. So each one of these commutators is normal in the original one. Wait, here he's saying it follows that Gi plus 1 is normal in Gi. Isn't that obvious since it's the commutator? Didn't we already show that the commutator subgroup is normal?
Gi is not the commutator of G. Gi is the commutator of Gi minus
1.
Yeah.
So Gi plus 1 is the commutator of Gi.
Yeah.
So doesn't that automatically make it normal in Gi?
Right, it is normal in Gi, of course.
So I don't know why he has to mention that it's invariant and that it follows that that's true.
Which implies that, wait. It is pretty easy to prove by induction that Gi is fully invariant.
I guess I don't care enough to get hung up on it for too long. I just didn't bother to look up what he means by fully invariant.
I don't know. I mean, I think like he says that like by induction, if you start from like 0, by the time you reach I, like it's going to be always the same. I don't know. Right, because you're like doing the commutator from the beginning, so I don't even know. But this looks like something we just are going to go through today, and I'll forget day after tomorrow, unless it's going to be in the P set. So yeah, this is, I think, different classifications of how you can build series. So this descending central series of a group is this gamma, which is like previous, but instead of like taking the commutator with itself, you're taking the commutator with G.
So with the derived series, the one that we just stepped away from,
Mm-hmm.
he uses that to give a different definition of solvable.
Yeah.
He says that a group is solvable if the derived series eventually lands on 1,
Yeah.
on the trivial subgroup.
Mm-hmm.
And he suggests some exercises showing that those two definitions are actually not identical. There's some groups that are simple under one definition and not under the traditional definition. So I'm willing to buy that solvable might be interesting.
Mm-hmm. Mm-hmm.
But then this thing with the gammas and nilpotent, I don't get that at all. Oh, but look, he's bringing up his unitriangular groups again.
This
So I'm
descending
kind of
central
with you.
series. Yeah.
I'm thinking that these nilpotent groups might be something that we see today and then forget tomorrow until they come up again. And I know who can decide whether or not to put those in the P set. That sounds like an optional problem to me. Hint, hint.
Yeah, because the concept itself looks optional, so the problems are going to be optional. A group G is called nilpotent if the lower central series. The lower central series. I don't know what this lower central series is.
I think that he means the same thing as descending, but I thought that was weird that he called it descending, and then on the next line, he refers to it as lower.
Oh, wow.
That's my guess, is what he means, because he didn't define lower central series, but he just got finished talking about descending.
Yeah. Y2 of G, so gamma 2 of G is G prime. But the derived series and the lower central series may differ afterward. For example, gamma 3 of G is a G prime with G, which includes G2 in the derived series, with strict inequality possible.
So when I did look up nilpotent very briefly, it squeezed nilpotent groups in between abelian groups and some other kind of group. It said that they're almost abelian in some sense.
What
So
keeps them
suggesting that it's an
abelian?
interesting group of groups. But I don't know.
Yeah, I don't know why they call it nilpotent. I mean, the nilpotent characteristic. The nilpotent characteristic is this, in the sense that the lower central series, I mean the gamma n, gives you 1 for some n, I guess.
I saw something about you can define some kind of operator, and if you do that operator enough times, then you get 0 or 1 or something. So nilpotent in that sense. Nilpotent over in rings meant that some power of it equaled 0.
Yeah.
So here, there's some operator. If you repeat it enough times, you get something trivial.
Mm-hmm. Okay.
Probably if we kept going in chapter 5, he might use it again. So I just noticed that in section 5.4, it starts introducing matrices, which I know are a kryptonite for you. So you jumped out of this book totally into a different book.
Kind of. I don't know. I just just found out, like, after this, like, he brings in the Jordan Moore stuff. I mean, I didn't see anything really interesting, which we would need. But
Do we see group presentations somewhere else in the course?
doesn't sound like to me.
Because I know that y'all probably worked with group presentations when you're doing algebraic topology. I mean, yeah.
Right, so he has 4, 5, and 6. The Nielsen-Schreier theorem kind of looks interesting to me. I don't know what he does there. He has something from the algebraic topology. Okay. The fundamental group. So, yeah. So Rotman, we're not going to do him until multilinear. I think if we had more time on groups, maybe we could have done that.
I don't know. I know you're eager to go look at modules, so
yeah,
it'd be good to hop over and look at that.
Yeah, modules.
It looks like the first section in. Oh wait, we're using Hungerford for modules, right?
Yeah.
It looks like the first section covers a lot of stuff. Just generalizing things about groups that we've already seen.
Yeah.
And in the second part, they start doing those short exact sequences or something. I think that's what those guys are called, right? Yeah, short exact sequences. They got some of those diagrams that you just were showing in line. So maybe this is a natural transition.
Yeah, you're right. So the first section seems quite. Oh, yeah.
Yeah, like that. Didn't we just see a picture like that in line for the current stuff?
Exactly.
Today's lesson. So I don't know. Maybe this is an inspired place to make the switch.
Yeah.
Looks dry though, gotta say.
This is Hungerford. You can't expect more.
I think that the material's just going to be dry.
Yeah, and it gets dry as we head to linear algebra.
Yeah. But I think that the proofs could be fun. Remember, some of these diagram chasing proofs are not bad at all. There's an art to it, so
okay.
It sounds like some good stuff.
Yeah.
Plus, I'm looking forward to getting back into Hungerford's exercises. I mean, he always has lots of good exercises.
Yeah, we've made like a couple of jumps, right? We got from Luffy to Arton to Dammit for rings, and we did Rotman. Yeah. Now Hungerford.
And we'll see Jacobson before the end of it. Oh, and Atia. Oh my god, Atia.
Yeah. Define a dimension. Okay, so this dimensional theorem relating to the division ring and the modules, that's one of the important things. We'll have to get that done. And
it was a good lesson. Thanks.
Yeah. So see ya. next Tuesday we're starting modules, and I'll send the pset for this soon.
Meanwhile, it's a little vacation between now and when we get the piece set. It's like the only little vacation during the week. This is like the weekend between Thursday's lesson and the piece set coming out, so no rush.
Yeah. Okay.
All right, have a good weekend.
Yeah, you too.